yeah, first I will just quickly introduce myself. So yeah, I'm currently working as an algorithm engineer at ADVANCE.AI, and I build deep learning models for EKYC and OCR solutions. Um, but maybe just some background. So I'm actually Burmese. I was born in Myanmar, but I've studied in Singapore since 2009. So it's been 13 years. And during my university, I had many great opportunities, like going to Canada for exchange. And also in my last year of university, I got to do a research thesis at MIT with a colleague group where I worked on deep learning for chemical synthesis planning. So yeah, just nice for my background as a chemist, as chemistry undergraduate. And last year in June, I graduated. And then I've been working at ADVANCE.AI since then. Yeah, so let's start with the presentation. So I think the first question that we should always ask ourselves is, why do you want to do something? Like, why do you want to predict energy demand? So always think about the business goal. And in this case, because if we have excess supply of energy, right, so if you are thinking about the perspective of the energy supply, right, if you have excess supply of energy, you're just wasting all of that energy. And at the same time, if you have excess demand, then you're gonna get blackouts, right? You're gonna get system problems, and your customers are going to be unsatisfied, like people living in buildings and homes. So obviously, if you want to maximize your profits, you want to make sure your supply is just meets the demand. So that's the business goal. And why do you want to use machine learning? Well, to be honest, in this project it was a competition, so we have to use machine learning. But in the real world case, you should always think about, why do you want to use machine learning, right? So the first question is, do you have enough data? But that's the most important question. And do you have lots of data, right? Because the point of machine learning is you have lots of data, and it's, as a human being, it's not easy for you to really understand all of the data by yourself. That's why you get the machine to do it for you. And in energy, we can use sensors to collect a lot of information, a lot of data. So that's why it's suitable for machine learning. And the context, as I've said, it's a competition. In fact, it's the first competition that I ever joined in summer 2020. And the data we've given was the temperature and energy consumption of a building at 15 minute intervals over 2 years. And it was provided by Schneider Electric. An objective is to predict the energy demand 24 hours ahead. And we were also asked to write an article and presentation. So yeah, we were very fortunate to win this competition. And yeah, I had a very great time with my 3 friends from NTU. Yeah, so now we're looking at time series forecasting, and something that I want to emphasize is that the concept of windowing, right? So every input into our model is actually a slice, a window of data from the past, right? As you can see here. And we're trying to predict some value in the future, which is the true value is a green value, and the prediction from the model is a yellow value. And you're going to have some error from this prediction. And you just keep doing this multiple times. And something you can also think about is, can we collect any extra information about the day that we're trying to predict, right? For example, is that day going to be a weekend? Is it going to be a morning, summer? Do we have any temperature forecast about that day? And all of this information, you can add it into your input. And this is obviously going to help the model to make a better prediction. So that's the concept of time series forecasting. And for the metrics, if you see this graph, you might think about the mean squared error, which is basically going to be taking the actual values minus the predicted values and square it. So for the predictions that are very far away from the true value, you're going to penalize them by a great amount, right? So this metric penalizes the outliers more. And something in time series something else in time series is autocorrelation, which is basically measuring how aligned your predictions are with your true values, right? Because you want your predictions to be on time, right? Which is basically a lag of 0. Because if you imagine your predictions are always late, right? They're always delayed by some time period. then it's not useful at all, right? Because it can be used in the real world. And also, we always think about the baseline, right? If we can't use machine learning, what's the baseline we could use to compare it? And here, the baseline is you just take the same value from 24 hours ago, and you just predict the same value as your prediction. So here you see the orange value is your test data, and your green value is your forecast. So you're just predicting the same value. That's the baseline. If your machine learning model can't even beat this baseline, then don't even bother about using the machine learning model. Yeah, so that's a concept of persistence. So now I have defined the problem and the metric. So these two are the most important things in a machine learning project. And now we can start to dig into the data. So let's analyze the data. And when we analyze the data, of course, we can start with the energy data. And we first notice some things about this. So the first is, if you look at the first 4 months, the data is really low. The energy consumption is really small. So we should actually remove such data because it's just too different from the normal data. And then for the rest, we can just split them into some training data and some test data. And something important in time series is you should not shuffle your data set, because you don't want data from the future to end up as a training data. And then you're just cheating, right, for your model. And now we try to dive deeper into some daily trends. And if we split the energy consumption by day, we saw a very interesting pattern that on the weekdays, it will always be higher than the weekends. So this already tells us that this building is maybe office building or school building. It cannot be a shopping mall. And so this information is very useful to the model. We can generate some feature called like whether the day is going to be public holiday or weekend, and we can give it a value of 1 or 0. And this is one kind of input that we can give to our model. And continuing this analysis, if we plot the daily trends for multiple days, we saw that every time at 7 a.m. it's going to start rising, and then at 6 p.m. it's going to drop. So this again kind of tells you it's an office building, right? And similarly, if you look at one day, we always saw this dip at like 12 p.m. So that's a lunch hour. So these are also features that you can provide to the model, right? Because these are signals that you can use to predict the energy levels. And another thing, this is more statistical, that we can get the autocorrelation values of the time series. It basically measures how correlated the time values across time. So you see that the value is the highest every 24 hours, which makes sense, right? Because at 12 p.m. every day, the building is going to have similar kinds of activities, and the energy consumption should be kind of similar. And also every week, the energy consumption also quite similar. So these are basically, it tells you the patterns in the data, and you can use these energy values in your training data, right? Because the energy 1 week ago and 1 day ago, they're going to be the most similar to the energy today. And also something in time series is we like to calculate the differences in the energy values, because the differences tells us the trend of the data over time. Yeah, so just to illustrate this concept more, so this is data of anti-diabetic drug sales. And if you look at the trend, the raw values, it has been rising over time. And if you want to capture the trend in this data set, you can take the difference, which is the plot below, and it just captures the differences. And this kind of data is actually more useful for the machine learning model than the original raw values. So that's something you can try for time series forecasting. And so now back to the data analysis, we have looked a lot at energy, and now we want to look at the relationship with temperature. So we see that here, there is an interesting pattern that the maximum energy demand, like these 3 green circles, always happens to coincide with the tail ends of the temperature. So we thought about this, and we did some Googling, and we found it's because of the need for heating and cooling. because in summer, you're gonna need cooling, right? And winter, you're gonna need heating. So at these periods, the energy consumption is always going to increase. So these are also very useful information that you want to tell the model, right? Whether it's the season winter or is it summer, and so we engineer these features. And we also plot that energy versus temperature, and we saw that there is some kind of quadratic relationship. Although I think in this, it's not really that quadratic, but at least you can still see the trend on a working day. And this is the same reason, right? The need for heating and cooling. So if the day is very hot, you want to turn off the air condition and the energy consumption will increase. And so the kind of features you can generate would be things like you want to take the square of the temperature, and that is one input. Or sometimes we can also take the product of the temperature and energy to get the interaction of the two variables. And this kind of data is very useful for the machine learning model. And in time series, of course, as the name suggests, the time is very important. So you can also think about the time data. And for example, one thing is time in 1D space is actually not very good from the model because, for example, in January and December, they are actually neighboring months. But if you look at the numbers, the number representation is 1 and 12. And so they're very far away, and this actually confuses the model. So you can actually try to transform it into some sort of space where there are neighbors. You can see the January and December neighbors again. And you can use this, you can do this using sine and cosine. We didn't just think of this on our own. We went to Google some papers and we read papers and we saw someone doing this. So we thought this is really interesting. And you can do this for day, hour, minute, and you can try to extract the temporal patterns better for the machine learning model. And so we have looked at the data analysis. And now I'll share about some data processing we did. So the first is that often in when you want to apply a model, you will have some missing values. So if you look at the energy data, you can see there are some gaps at regular intervals. And it's quite big. It's maybe 1 week of gap. So you need to think about how to deal with this. So the one naive idea is you can try to do some linear interpolation. But actually, this is wrong because, I mean, if you just look at the pattern, it already looks wrong, right? Because it doesn't match the trend in the other days. And also, it causes the problem of data leakage because if you think about it, you're going to take data from the future in order to do some linear interpolation. And in time series, you should never take things from the future. So that's the data leakage. And the idea we came up with is basically taking things from the past. So if you have some data that's missing on a Monday, then maybe you can just take the previous Monday's value and just copy the same data. So you just respect the time of the day, and then you just copy the same value. So if it's a Sunday, you're going to take the previous Sunday's value, and you're just going to copy it. So actually, we found that this is much better for to respect the temporal trend in the data set. And also the result, the model performance is also much better. And for the temperature itself, we just did a simple interpolation because here it's kind of different because we have a lot of temperature data. It comes at every 15-minute intervals, and we just want to change it to 15-minute intervals. So it's just a matter of just interpolate between 30-minute intervals, and you can see the trend is the same. So it's okay to do the interpolation for temperature. And another thing we did is normalization. I think if you are already in machine learning, you should know this. Like we just want to make sure that all the features have equal contribution to the model. Like here we see one feature, the magnitude is like 500, 1000, and the other one, the magnitude is like 0 to 1. So you want to make both of them have the same effect, then you should scale both of them to the same scale of 0 to 1. And you can use like min-max normalization. There are lots of normalization available. And you just use one and for every feature. And that's how we normalize the data. And also in time series, something that you can try to apply is to predict the difference instead of the raw values. So it's, I already mentioned this before, that the difference focuses on the trends. And this is actually better for the machine learning model. that you want to predict the difference of the values rather than the actual values. And I see a lot of time series projects doing this. So we also try it, and it works better. Yeah, so you can see if you plot the distribution, the green one is all the differences, and it's more evenly distributed. If you just look at the red one, the raw one, of course, it's all going to be positive, right? And it's more uneven. It's harder for the model to learn. Yeah, so that's about the data processing and analysis. And now I talk a bit about the model iteration. But actually, I want to emphasize we actually spend the least amount of time to iterate the model, because my own principle is we always believe that the data is more important. So here I just focus on the principle that you always go from big to small. And so you start with some large neural network, like maybe you start with like 5, 6 layers, and you add a lot of neurons, and you try to see the performance. And if the model is overfitting, then you try to shrink the model and make it smaller. And that's how we iterate the model. And in the end, we come up with this model. It's quite simple. It has 4 layers. It has maybe 30 neurons in the first layer. And we use the mean square error loss, same as the metric. And we use the Adam optimizer. Right? These are quite simple settings. And for the feature selection, I do want to mention we did something using the Sharp library. Basically, the Sharp library is we try to get the importance of different features. Right? Because if you think about it, when we brainstorm initially, we have lots of features. Actually, we came up with like 300 plus features. And we have to do some shortlisting. So we did some initial experiments. We tried to discard the useless ones. And then we train an XGBoost model on this data set. And we try to get the feature importance using the Sharp library. The Sharp library can get the feature importance using some game theory concepts. I didn't really care about the details, but it's quite a good library. So you can consider to use it and get the feature importance. And we just take the 50 top values that it ranked. And then we just do some further experimentation, and we get the 36 features. And this is the best set of features. And for the results, we saw that it's quite good. We can beat the persistence baseline by 53%. And of course, the lag I mentioned, the lag should be 0. So we see in the green section, the performance is actually very good. Later, I will zoom in, but in some period like late winter, actually it wasn't that good. Yeah, so I'll zoom to the prediction, and you see the good part. So you see in the green box, the prediction is the blue line, and the actual is the red line. You see, actually, it's very, very good. The performance is like almost perfect, I would say. So that's very good to see. And even on public holidays, you see that it still predict a low value. So this, I guess it could be because we made those features, like whether it's public holiday, whether it's a weekday, and those things. So these features are helping the model. And we also see in another time period, it's also very good. But we also saw in some other period, it's quite bad. But actually, we thought about this. And if you look at this data, these are weekends. And weekends, somehow the actual value was very high. So this is kind of anomalous, because if you think about an office building, on a weekend, everyone should be at home, right? So kind of we think that these are anomalies and kind of hard case. So it's hard for the model to predict these well. So in this case, maybe we shouldn't blame the model, but we need to look into the data instead. And yeah, just to spend some last slides. So I mentioned the use of the Sharp library, and you can actually use it to explain to get the feature importance. And actually, the same library you can use to explain your model, because you want people to understand why your model makes certain predictions. And so we use this model on the XGBoost that we train with the 36 best features. And we found that the highest ranked features actually make sense. For example, the time features are actually very important, like whether it's a working hour, whether it's a day of the week. So this makes sense, right? Because these are very important for you to tell the energy. And also some features like the interaction between the energy and temperature are also quite important. And lastly, the difference that I mentioned, right? You want to get the trend in the data set. The difference features also quite important. So yeah, this is something that that we applied and found quite interesting. And so on a final note, I want to mention some limitations we had. For example, we had I think the test data we use is probably not enough. We only had a few months. So ideally, when you want to apply onto a real world data set, you want to have lots of test data. You want to have 1 year, 2 years test data to make sure your model is really working. And also, I feel the data source we had was not a lot. Yeah, so can we collect more data? I think that's something we always think about. Like, for example, can we collect rainfall data? Can we collect humidity data, wind speed data, and so on? Yeah, and also the feature selection part, I feel it was maybe not very efficient because we did a lot of experiments to manually try different feature combinations. But actually, we found later after the competition, there's some library that can do it for you. So maybe we should always try to find ways to automate our projects. And another thing is, because it's competition, so we had time constraint. But actually, we can consider not just neural networks, but right now everyone is trying transformers. So maybe we should have tried transformers, right? It probably will do a lot better. But of course, you need more time to write the code and things like that. And also because we're just beginners, so we didn't really have the domain knowledge about what is energy forecasting. So I think that kind of thing could really help. And the last thing I want to point out is the geographical constraint, because you should always think about the data, right? I think this is just one building. So if you want to apply this model to another place, another building, it probably is not going to work because it may be in a different country, like Singapore. The weather is going to be very different. So this model actually is, to us, actually is just an MVP, I would say, that it won't really be usable in the real world. So these are some constraints that you should also think about in your own projects. And yeah, with that, that's the end of my slides. I hope that it was useful. And yeah, here you can check out our article on towards data science. You can scan the QR code. And if you're also interested, actually we joined another competition, which is on energy production forecasting. And you can also check out the QR code if you're interested.